Hi there. In this video, we're going to display the TDR pulse on two separate oscilloscopes. The first oscilloscope we're going to use is the Tektronix 547, that's on your right-hand side, the one that's closest to the workbench. The second oscilloscope we're going to use is the Tektronix TDS220. It's that little white oscilloscope that's on my desktop just above the ESI there. Alright, on to the video. Here we have the Tektronix Type 547 oscilloscope from way back in the 50s, 60s era. It's full of vacuum tubes, it's forced air cooled, it's got a big furnace air filter on the back of it. It's belting out hot air and cooking me out of my lab right now. It's a pretty hot piece of equipment. It's running. It has a thermal sensor inside, so if the fan plugs, the thing shuts down because of course the tubes would just bake this thing up right now. Incredible amount of tubes inside there, and it even has some transistors. So they're comfortably working together in this thing to make this pretty trace that we see on the screen here. Pencil thin line, you know, really high accelerating voltage, so there's lots of brightness in this oscilloscope. And it wants to show its stuff. It says, hey man, I can keep up with today. It's going to try and look at this 900 picosecond rise time out of this little TDR head here. So, and 3 nano fall. So it's going to try and show its stuff. I'll show you the plug-in unit. It's a 50 megahertz bandwidth oscilloscope with a 50 megahertz plug-in. And of course, being Tektronix, it exceeds everything. It's just, you know, they built that right into their design. So this is the plug-in, the 1A2, one of my favorites. This is the TDR head here, and it's being CT'd into channel 2. Channel 1 has a probe on it, so we'll just use channel 2 here. This is time base B, and this is time base A on the top. And we're going to be using time base A just because. No particular reason, just because that's the one that I chose to use. So right now we're at 2 milliseconds per division. That's going this way on the graticule. You have to use a graticule on these old oscilloscopes. You can't, there's no on-screen display, you know, there's no trigger level, tell you where your trigger level is. You all have to set this all by, you know, manually by hand, and it takes a little bit of brain power to use these things, but once you're used to it, yeah, they're a breeze. And they're really, you know, these old scopes are very accurate. These are the absolute Cadillacs of oscilloscopes. So, and you'll see that here to come quite shortly. So, this is too slow, 2 milliseconds per division. We need to put the pedal to the metal with this thing. You know, we got to turn it right to the max, right up to 0.1 microseconds per division. Okay, that's very fast for this scope. That's the absolute max this scope will do. And we have to turn the brightness up, of course, because it's so fast the trace gets a little dim, but now it's bright again. We still have tons to go. As you can see, we're just at number 6 here, a little bit below it. So we'll turn on the TDR now. We can already see the pulse at 100 nano. 0.1 microseconds per division is 100 nano per division. So that's in today's speak, 100 nano. So I'll move the vertical position down here and turn the intensity up just a little bit more, and look at, we can see that signal absolutely perfectly. So now this probably looks really bright in the camera, but it's not very bright here. It's about, you know, comfortable for my eye, and that the camera is really sensitive to this phosphor, so that's why it's going to look really bright in the camera. So 100 nano per division is okay for looking at really long chunks, but you know, we have shorter pieces of coax, so how are we going to do that? Well, Tektronix, they included a magnifier. It's really cool. It's a sweet magnifier, and it has a ×2, ×5, and ×10 position of what you're at. So what we're at right now is 100 nano per division, right, going this way. So ×2 is 50 nano per division, ×5 is 20 nano per division, and ×10 is 10 nano per division. So let's just crank this right up to ×10, which is 10 nano per division. We'll move this back over onto the screen here, and there's the TDR pulse. Look at that. Look at how nice that looks. It's at 10 nano per division. It's beautiful. We see that TDR pulse, no problems. You know, and this is a limited bandwidth oscilloscope. No issues whatsoever. Gets even better. Got a piece of coax here that I've measured to 52 nanoseconds round trip time. It's a piece of coax here. Another piece of this Fujikura coax. I've got lots of these jumpers, and they're just randomly cut to different lengths, and somebody crimped BNCs on the ends here, so let's plug this in. So there we have it. This is the TDR pulse here, and this is the reflected open end. So now let's check the graticule for accuracy. We know that this is 52 nanoseconds round time, so I'll move this over just a bit. Very touchy controls because the magnifier is on, right? So it's magnified to the max right now. We'll call that, get it as close as we can to the graticule. It's a little bit touchy. There we go. So we got 10, 20, 30, 40, 50, 2. Look at that. It's like spot on. Can even move it over just a hair. There we go. Try and get as touchy as I can. It's, you know, the magnifiers on those controls are really touchy. There you go, 52 nano round trip time. So yeah, as I say, you know, this is a 52 nano complete time, 10 nano per division. So we got that 10, 20, 30, 40, 50, and 2. So pretty accurate for this old oscilloscope, and it's still, you know, is a relevant piece of test gear to this day. And that's what Tektronix did. They took oscilloscopes from the qualitative measurement area and put them into the quantitative measurement area, and that's what we have here. Even at max time, max magnification, this thing is still accurate. You could use this as a velocity factor test or a distance default test and get very accurate results with this. So there you have the old Type 547 oscilloscope still showing off to this day. No alignment. I've done no alignment on this scope, and I don't know of any alignment that's ever been done to it. As I say, when I got it, all I did was blow the dust out of it and lubricate the fan, and it's been running ever since. Not even a single tube I've changed inside this. So all those myths about these things being hard on tubes and that kind of stuff is just, it's all myths. So I have lots of these old scopes. I have another 547 here and a 565 over there. So, and none of them have any problems. I haven't replaced a tube in any of them. So, maybe I'm just lucky. Sure is a handsome oscilloscope. Now we're going to look at a TDS 220, which is a new piece of plastic with an LCD screen on it. It's 100 megahertz bandwidth, and it's digital. Nowhere near as exciting as this beautiful oscilloscope, but we'll look at it, and we'll check out the signal on it. So I'll see you over at the DSO. Here's my little Tektronix TDS 220 digital scope. It's displaying the TDR pulse with ease on the screen. It's a 100 megahertz bandwidth scope. Works really well. It's never given me a day of grief. Every time I turn it on, it works. It's been really dependable. It's never glitched out, never done anything. It's been a really good piece of gear. The BNCs on the front are still tight, and the probe compensation's all tight, so it's seen some pretty heavy use. You know, the knobs have got some cracks in them, I guess, from age. The plastic's drying up or something. I have no idea, but ever since I've owned this thing, though, one little thing that did bother me is there's a lot of side play in all these knobs. And I'm beginning to understand that all the new DSOs are being built like this. For what reason, I don't know. Maybe it's a manufacturing thing, or maybe nobody's complaining about it, but it sure does feel cheap. But it's the norm nowadays, whatever normal is nowadays. So 5.0 nanoseconds is the time. That's as far down as this scope will go. It won't go any further down, which gives us adequate width on the signal here, and we can back a reflected right up to the fall time here and look at a signal with absolute ease with the scope. So I've got a piece of RG8 stuck to my bench here, and I'll use that. All my coiled rolls want to pull this thing forward, so this here just works really good and holds it in the shot for the video. So that's why I'm using this big piece of coax. It's a pretty mondo piece hooked up to the front of my oscilloscope, and yes, they're still tight. So anyways, there's the TDR pulse. I'll turn this to 10 nano, and I'll center this on the screen here. And we'll turn the cursors on. And the vertical controls now control the cursors. This controls this cursor, and this guy controls this cursor, so I'll just roll them in. And roll this one in. There we go. 47.2 nanoseconds is a round trip time of this coax. So if you've watched the distance default video, you'll know how to calculate the length of my random piece of RG8 hanging off of the front of my oscilloscope here. The incident edge and the reflected edge, again, you can use that if you want, but using the peak will give you the same time. So you're just absolutely fine, and you'll get very, very close to your target measurement there. So that's the little digital oscilloscope, and this is also the last video in this series on this TDR. So if you liked it, you know, give it a thumbs up and subscribe, and you'll get lots more interesting videos. I plan to hit on all sorts of different kinds of topics, not just stuff with oscilloscopes. So we'll go into transistors and vacuum tubes and theory and all sorts of crazy things here in the future. So if you enjoy this stuff, stay tuned, and I'll see you soon.